Welcome to this third lecture in the Structural Dynamics course, and today we are going to look at basically a lot of different loading conditions, and the one thing they have in common is that they are not harmonic excitation. So transient loading is a general type of group of loading conditions that are non-harmonic. But in particular today we're going to look at impact loads and also so-called box loads that are impact loads with a somewhat longer duration. So within this type of transient loading conditions, you can actually find quite a lot of real physical problems that can be solved by these solutions that we're going to consider today. The generic transient load is the impulse. So you have a structure, it could be in a sense maybe a horizontal bar or beam, and then you snap it by a fast load and it deflects violently and vibrates forth and back, and because the loading P here is very fast with respect to time, it's more or less just an initial velocity. So what we are going to consider today is what's the relation between an initial velocity and this impact. And the idea is, of course, that the conservation of momentum is the key aspect. So once we have decided on how we're going to represent an impulse, we're going to apply it to a structure and see how this vibrating structure will react to a very short and intense load impulse. And mathematically speaking, it can be modeled by a so-called delta function, which is a very particular and very convenient mathematical function that represents the ideal impulse quite good. And once we have modeled that, it's actually possible for us to derive the response to this transient load, and also based on a short duration impulse. And we'll have a look at how this short load, which is also often referred to as a box load, will excite the structure. The idea of having a transient response, as we indicate here at the top of the slide, is basically that the response is non-periodic. So the reason why we look at impacts is that the total response can actually be considered as a superposition or an addition of the response when the non-periodic loading is divided into small pulses, a sequence of pulses. And if we know how to find the response for a single pulse, we can find the total response by simply adding the response for each individual impulse, based on the principle of superposition, which is of course only valid for linear structures. So if you have nonlinearities in your problem, this principle will not be applicable. So let's dig into the notion of a load impulse or just an impulse. So Newton's second law states that the change in momentum is in balance, or refers to the force exposed to this particle or mass. So we will consider our typical mass m, then we will expose it to a load F, and this will generate a velocity v in agreement with relation 3:1, where we have that the change in mass times velocity should be equal to the forcing term. And this differentiation that we have on the left-hand side indicates that if we want to obtain velocity, we should somehow integrate this relation here. So let's decide that we integrate from t1 to t2. And that means on the left-hand side, we will have m times v from t1 to t2. That is, of course, the difference between the momentum at t2 and the momentum at t1, stated like this. On the right-hand side, the corresponding integral is the integral from t1 to t2 of the applied loading. So for the time being, let's refer to this integral as f hat. Of course, this depends on how the forcing looks, but let's assume that we have, that wasn't very straight, do it more accurately. Let's assume that we have time and we actually want to represent our loading, and we have some kind of impact loading from t1, which is equal to 0, up to t2. So the integral f hat in this case simply represents the area underneath the loading curve within a force time diagram. And this integral f hat we will simply refer to as the impulse, because it governs the change in momentum from t1 to t2. If we have the possibility to divide by m, if m is known, then we will actually on the left hand side identify the change in velocity, or simply the velocity increment delta v, increment here, and it's given by delta v. And this of course means that over time from t1 to t2, if we have some form of change in f, this will result in a change of velocity of our particle. So we're already on our way to rocket science. However, let's leave rockets and consider structures instead, because the difference is of course that our structures are at least mostly suspended to the ground by some form of stiffness, and we might even have energy dissipation in the term introduced by the dashpot representing damping. So for our structure, we do not only have mass, the time derivative of mass times velocity on the left hand side, we will instead have the full left hand side of our equation of motion, not only the first term, but we'll also add a damping term and a stiffness term. And on the right hand side, we apply our loading. So we like today to consider what if this load here is actually initially a short impulse, but in general, what if it's non-periodic? How do we treat the analysis of such a general transient loading on our structure? But let's initially go with the short impulse on our structure, as also indicated in the title of this slide. So what we do is that we initially integrate over time, according to the procedure we had on the previous slide, and let's again integrate the left-hand side and the right-hand side of a time integral from t1 to t2. So the acceleration term is converted into a velocity term, and it's again represented as the change in velocity from t1 to t2. So it's velocity 2 minus velocity 1. Then we also integrate the damping term, and velocity integrates to a change in displacement, while the stiffness term, we keep that as the integral of the displacement, including the stiffness. On the right hand side, we have the integral of force, and this is provided by the hat notation. So for a short impulse or short loading duration, this will be our impulse identified on the previous slide. Now, try to follow this argument. Let's say that you have some kind of characteristic magnitude of the acceleration. That means if you integrate over t2 minus t1, then you will actually have acceleration which is constant, at least we assume, and then the integral will give us delta t. So here delta t is t2 minus t1, and we will consider that as a short time duration. If we then integrate velocity to get displacement, then we will get constant acceleration again, and then 1/2 delta t squared. If delta t approaches 0, that means again representing a short impulse, then we will have that displacement is smaller than velocity, and velocity is smaller than acceleration, simply because of delta t and delta t squared. So this basically shows that for short impulses, the damping has not really evolved, and stiffness, because of very small displacements, plays no significant role. So the only term on the left-hand side for short impulse durations that is non-vanishing is the mass times change in velocity, and if we remember from the previous slide, we will have that the change in velocity we can refer to as the velocity increment, and we've divided by mass, and the integral is equal to f hat, giving us that even for the structure, not only for the rocket particle, but even for a structure suspended by stiffness and damping, the change in velocity is entirely governed by basically particle physics. So it's the momentum divided by mass, where f hat is equal to the area underneath the loading curve. So by this analogy and these assumptions, we have transformed a loading condition with a right-hand side that is non-zero, and we've converted that into a problem of a change in velocity. And that means we can basically go back to our lecture number 1 for free vibrations and use the results with an initial velocity to represent the short impulse loading condition on our structure. So have a look at on the figure, and the figure contains two things. Of course, mainly it contains the displacement, but we will also allow ourselves to, in these figures, to indicate the at least time dependency of the loading in our problem. And because the x, the vertical axis represents displacements, you cannot, of course, say something about the magnitude of the loading here. But you see, it's quite short. It's maybe 1/10 of the period, and that means we have a very short impact loading on the structure. And we know that the area underneath the F curve is actually the same as F hat. So let's raise this one here. And the response, you see, is at time equal to 0, an initial inclination that provides us with a harmonic displacement. So the initial displacement x0 is equal to 0, whereas the initial velocity is equal to the change in velocity that we have from f hat divided by m. Suddenly we can do transient impulse loading analysis without actually solving the inhomogeneous ordinary differential equation. We simply convert the normalized area underneath the loading curve into an initial condition. And what should be mentioned here is that you see, to get the best result, you see that the load box is centered around time equal to 0. So it spans from a little bit below to a little bit above time, and this increment here we will then consider as delta t. So the area underneath the curve is equal to the magnitude of the load times this width of the loading box, which we'll assume is delta t. So for vanishing initial displacement, we will simply have an initial velocity where the plus indicates that it is a velocity that is due to the impulse loading in our case. Go back to lecture number 1 and find yourself the solution to the damped free vibration response with initial displacement and initial velocities. Then you take the initial displacement and set that equal to 0, and what you will find is this remaining term containing the initial velocity, the damped natural frequency, the loading, the exponential decaying function due to damping in the system, and you will have a sine curve that governs the harmonic. And in the above figure, we will have that tau is equal to 0 in this figure here, but in principle, the short impulse could also be applied at time that's tau equal to 2 seconds or any other impulse time. So we will take V0 plus and replace that by F tilde M. So what is left is the 1 divided by omega d. It is the exponential function, it's a sine function. And this green function, or function in the green box, we will denote as h, and h is commonly referred to as the impulse response function. That is the solution to x when you apply the normalized impulse by the mass of the structure. And the impulse response function is therefore defined as the expression to the right in the blue box in 3.10. And if you look at the figure in the upper corner, at the top of the slide, this figure actually represents the impulse response function. If we divide by f tilde m, and I'm pretty sure I've plotted these functions so that is the case, so you could actually write m divided by f tilde in this curve and normalize the x solution by this way. So this is actually minus 0 in our case because we initiate tau at equal to 0, so it's just the impulse response function with respect to time as shown in this figure. You can actually use the theory behind impulse response functions not only to replicate the response due to a very short impact, but you can actually also use it to solve general response solutions to general loading conditions. So the idea is, in this case, that a short duration load can be represented by f hat, that is the integral underneath the loading curve. Let's assume this is what you found for this smooth f curve that you see in the upper right figure. What if you want to represent that by a box load and therefore be able to use the impulse solution that we had on the previous slide? The question is, of course, how should you draw this impulse box? Now, in this figure, in the middle figure, it has some width. Let's call it 2 times epsilon. And to retain the area between these two curves, the height should, of course, be the area f tilde divided by the width 2 epsilon. And that could give us a fairly wide box load as indicated in this figure here. Now, what if we halve the width and double the height? We still have the same area, that's f tilde, but suddenly the impulse becomes much more spiky. And we could continue this exercise. And at the end, in the limit, we would have an infinitely tall spike, but with a width that is equal to 0. And don't show this to mathematicians, but this infinite times the width 0 should then be equal to f tilde, because the area underneath this curve is the same as in the first figure with the f tilde that we want to represent. And we actually have a name for this very idealized function. We refer to this as a delta. And we have time here, and we spike the function at t equal to 2 tau. So this delta function, or Dirac's delta function, is actually used to scale our loading condition. So it represents the impulse load when we take the area of the impulse load and we multiply it by this delta function. That means that the delta function is actually the spike, but it does not integrate to f hat, because f hat is already present in our problem. So if I integrate on both the sides, I'll get ft, and then I'll get f hat, and then I'll get the integral of t minus tau delta t. And since this integral is equal to f hat, then the integral of the delta function should be equal to 1. So the delta function, or the area underneath the delta function, provides the spiky appearance of the load, whereas f hat defines the area underneath the curve, and thereby f hat retains the momentum balance for our short impulse. And the delta function is extremely convenient because not only does it integrate to unity, when multiplied to some kind of function, it actually provides the value of the function when you insert tau. So the argument of the delta function here is equal to 0 for t equal to tau. This simply defines where the spike occurs in time, and that means that you substitute t equal to tau into the y function. So this is actually the solution to the integral of a delta function multiplied by any function. And this, of course, could as well be some kind of loading function or shape function or anything. And the response to transient loading is then simply an augmentation of our theory for impulse loading. So now we consider more general types of loading patterns. Let's assume that you have a loading that is represented by this blue dashed curve. So this is simply the expression for f. The plot itself represents the deflection of our structure. Now, the idea is that yes, our blue dashed curve is a quite complicated, non-periodic, general type of loading, but it can be divided into small sequences. Let's assume that we are at tor I in the curve, and at this position here, we will have a box load that is very short, and we will have a hat at this time I. So we can go back and we can find the response from this very short impulse by dividing with m and multiplying with the impulse response function. And that is because we know the solution from the blue box for a very short impulse with area underneath f tilde for structure with mass m, and then we simply multiply by the impulse response function. So at time equal to I, we find, or we don't see it, but the subsequent following mathematical solution to the displacement is here illustrated by the magenta curve, which I overwrite in green. Then at some later time, tor j, we have a different loading magnitude, and that means that our f hat j becomes different than f hat I. But the solution for this short red f hat is then again given by the impulse response function, but because the red area is larger than the green area, the amplitude will be larger, because f hat divided by m is larger for the red curve than for the magenta / green curve. So the idea is that the total response is then simply the sum of all responses when we split our blue dashed curve into small parts. So for all these small parts, we will have an oscillatory solution that is given by f tilde divided by m multiplied by the impulse response function. And what we should remember is that the initial time for each of these solutions is shifted by the width of our loading box. So once we do the simulation here, all of these contributions do not start at the same time, but they are shifted by the delta tors that are given in here, which also determine the area underneath the curve. So we simply split the loading curve into a sequence of small impulses, find the solution for each impulse, and then we make a summation like this, and that means we have a superposition of the magenta curve and the red curve. So for instance, at this point here, we'll have the sum of the red curve and the magenta curve, and all the other curves that have been initiated by all box loads appearing before this time a little bit less than 3. And if you simply do that, you can see that the blue curve here is given by the sum of all these box loads obtained by the impulse response function, whereas the dashed solution is the exact solution obtained by simply numerically integrating the full equation of motion using the time step function that we have implemented in our software package. So you see that the sum of impulse response functions gives the exact solution. Now, what if we decrease the width of these loading boxes? So for instance, a box like this up here has a certain width, delta tor. What if this approaches infinity, or 0, sorry. And when delta t approaches 0, then the sum approaches an integral. And this integral is then the integral from the beginning of the solution, that could be 0, up to current time t, which could actually be at this point here, where we have the response x of t. And that means that we should integrate from time equal to 0 and all the way up to our time t. So that is, at least for long simulations, a quite elaborate way to obtain the response. Because when I advanced my simulation and now I want to move to the next data point to find this response here, I should again start from 0 and integrate all the way up to my new time t plus delta tau. So this Duhamel or convolution integral solution to obtain the response is exact. It's quite effective if you have short, medium size, length loading conditions, but for longer analysis, let's say a large structure placed in the North Sea exposed to wave loading, and you're going to analyze for 30 minutes, maybe a couple of hours, then it's quite numerically expensive computational wise to use this convolution integral approach, because you in principle require so-called infinite memory. So for each time step you need to integrate all the way back from time equal to 0. More modern and also efficient type analysis, instead using so-called single-step time integration procedure. This is actually what is used in time step, where you can advance from one increment to the next increment without remembering all the states back to time equal to 0. And in this course we will also consider the so-called Newmark method, where we can solve large coupled equations of motion, dynamic equations of motion, by this single-step procedure. If you go back to our lecture number 1 on free damped vibrations, you can actually organize your solution to x as all terms proportional to initial displacement and all other terms proportional to velocity, grouped in two groups. So everything that is multiplied with displacement is the so-called initial displacement function, while the h function will be your impulse response function. That means if you have no initial velocity and only an initial displacement, you should plot the g function, which we've actually shown in I think in lecture number 1. So it starts out at unity, and although it's difficult to see, it has a horizontal tangent, and then it represents a decaying harmonic behavior according to the S-Dov free vibration theory from lecture number 1. So that's our initial displacement function. The initial impulse response function, or initial velocity function, has initial displacement, but it has an initial inclination representing the initial velocity, and it has its maximum point at a quarter period later, and then it experiences the same type of exponential decay as we have for the g function to the left. So they both represent either initial displacement or initial velocity solutions. Functions are given here. The initial displacement function is a little bit more elaborate because it contains both a cosine and a sine, whereas the impulse response function only is a sign-dependent function. And there's a very nice property, namely that the derivative of the initial displacement function is proportional to the initial impulse response function with a factor of minus omega 0 squared. So in the bottom curves, when we have normalized this by omega 0 and time is actually also normalized by t, then we will have an initial curve for this part. Let's have a look at an example. So let's have a look at the curve. So for time equal to 0, we then suddenly apply a constant load. So let's consider, although it's not a single degree of freedom system, let's consider you have a beam or something like that, and you take some form of weight, and at time equal to 0, you place your mass on the beam, and that means at time equal to 0 you apply a load that is equal to gravity times m. Well, let's have a capital M here, just so that we do not state that this is the structural mass. It's some kind of weight we apply, and then we have some form of deflection, and it vibrates up and down, and that's damping in the structure. So the loading here, Fp, could be G times some kind of weight M, and we apply that at time equal to 0. We divide by mass, so on the left hand side we get our damping term and the stiffness term represented by omega 0 squared, and on the right hand side we will have our loading P divided by M. In this case, as for the harmonic analysis in lecture number 2, it turns out to be convenient to divide Fp not by the mass of the structure, but by the stiffness. And then we have stiffness divided by mass as a factor, and that means we'll get Fp divided by K times omega 0 squared. And this Fp divided by K we introduced in lecture number 2 as the tilde times omega 0 squared. So it's the static deflection due to this gravity load that we apply on our structure. So we can represent the right hand side as omega 0 squared times Fp tilde. It's simply another way to write Fp divided by M. But from the point of the solution, it's a good idea to normalize it this way initially. We know that the full solution is given by a particular solution times the homogeneous solution. And the homogeneous solution is conveniently represented by the initial displacement function and the impulse response function. So we simply need to determine the initial displacement x star and the initial velocity v star based on the actual initial conditions, namely that the displacement and velocity at time equal to 0 are both equal to 0. Let us take the expression in 315 and substitute in x of 0. That gives us Fp tilde plus x star and G of 0 plus V star H of 0. If we go one slide back, then G at 0 is equal to unity. And did I write? Have I indicated? Oh, I better correct this. So have a look. Sorry, let's go back a little bit of time. So the inclination of the G function is equal to the value of the H function. So that means at time equal to 0 you will have a slope equal to unity. And the value of the G function at time equal to 0 is equal to unity. Whereas the value of the, and also it has a unit, a zero slope, because the value of the H function at time equal to 0 is equal to 0. So I substitute these two values into my expression and get F tilde, Fp tilde plus x star, and the last V star term vanishes because H at 0 is equal to 0. And according to the initial condition, this should be equal to 0. That means that x star is equal to minus Fp tilde. Then I differentiate 315, so I get x dot of t. That means I should take the derivative of Fp tilde, and Fp tilde is independent of time in our case, because we have a constant applied load that is equal to G times the weight of our mass. So this disappears, and we will get x star times the derivative of G time equal to 0. But this vanishes because the derivative of G is equal to the value of H, and that means the derivative is equal to 0. So that's why this term will cancel, and what we have left is V star times the derivative of H, and the derivative of h is equal to the inclination of the impulse response function, and this inclination is not equal to 0, and therefore this is the only term out of 3 that prevails the time differentiation, and our initial condition states that the initial velocity is equal to 0, and therefore we have that v star is equal to 0. So if this term cancels and x star is equal to minus fp tilde, then we will get this x solution in 3.16, which is shown in the figure underneath. So at time equal to 0, when we apply the constant load, we will have an initial increase in the amplitude, get a response that is in the normalized sense here almost equal to 2, and then we will have a damped decaying response centered around the static deflection here, that is fp tilde. So the vibrations will slowly die out, and at the end we will have a deflection of our structure that corresponds to the case where we very slowly and calmly softly apply the weight on our structure. And that also makes good sense. But you see the devastating part here, that if you apply the load suddenly at time equal to 0, you almost get and double up in amplitude. So if you calculate the stresses statically, you should actually multiply them with 2 to be able to represent this almost 100% overshoot due to the static behavior. And the smaller damping we get, the larger or we will approach a full 100% overshoot. Now we can start to play around with our newly gained knowledge about how we apply constant load, because together with the property of superposition, we can suddenly start to build what we refer to as box loads. So the final case is actually shown on the figure to the right. We would like to apply a load that is constant over a certain time instant. Let's say that the load begins at 0 and it terminates again at Tp. That means the entire box duration, load duration, is here Tp. So the way we're going to solve this is that at time equal to 0, we are going to apply a constant load with a positive magnitude that is equal to the magnitude we also want to apply in our Tp load. The problem is, once we reach Tp, we should actually cancel all the load that is beyond this time limit. And we do that by applying an opposite load of the same magnitude, which is also constant, but simply shifted in time by Tp. So from the blue load, we'll get the solution that we got on the previous slide, and in fact from the red load, we will as well get the solution that we got from the previous slide. Just for the red curve, it will be negative, and it will be shifted by Tp relative to the blue solution. So the blue solution is 1 minus G, where we start at T1 equal to 0, and the magenta solution is equal to minus 1 minus G, where the T2 solution will be at Tp. And that gives us the blue and the magenta curve that we see in the left figure. And the final red solution in the right figure will actually be the sum of the blue solution and the magenta solution. And if we set that into the solution, we'll get G and then T minus T1 minus G for T minus T2. Let's assume that the time difference is between T1 and T2 is not that big. That means we can actually approximate what is inside the square bracket by a change in G over the time instant. Now, if I divide by Tp and I also multiply by Tp, and then I introduce F tilde as Fp divided by K, I can actually, for small time instant, consider delta G divided by Tp simply as the derivative of the G function. So it's a change of the function divided by the change in the independent variable, which which is time. And the derivative of g we know, because the derivative of g is equal to minus omega 0 squared times the impulse response function. So we have minus, and then we have minus omega 0 squared times the impulse response function that is centered around the around our box load, and we'll then have Fp divided by K, and then we'll have Tp. Now omega 0 squared divided by K is equal to 1 divided by mass, and that means we'll get the impulse response function, we'll divide by mass, and this one here is basically the area underneath our box load. So this is referred to as the impulse. So as you can see, for a box load, we recapture the solution from the impulse response function, and that is because we have assumed that the Tp value approaches 0, because that is what we need to assume, that this fraction in the red box is equal to the gradient of the initial displacement function. But the exact solution is given here as the difference between the two g functions. Now, how well does this impulse response function actually approximate the correct solution? So the correct solution is actually the red curve. So that is the g minus g function that we see in 318 before the approximations. Whereas the dotted solution corresponds to the approximate solution using the impulse response function. And in this case, they actually match quite well. Do we have an overshoot of maybe 10 to 20%, 10% maybe in this case? But remember that for this case, the Tp function seems to be within 1/4 of the period. It's actually exact 1/4 of the vibration period. If we were to extend Tp so it became half of the period, or maybe even a full period, then this approximation here, leading to the impulse response solution, would way overestimate the amplitudes of the maximum deflection we would see, and if you were to use that for your structure, you would over-dimensionize your strength of your structure and spend too much money on it. So one could definitely argue that the solution using the impulse response function turns out to be an upper solution for our problem with the box load. But the box load can quite easily be solved by simply superposition of shifted solutions for the constant load problem that we had on the previous slide. So, of course, the load duration has an impact on the accuracy. So let's have a look at different load durations, and we're going to use simulations by the time step algorithm to find the exact solution. So the exact solution in our case is then given in blue, red, and magenta in the figures below. So the blue curve actually represents a fairly short impulse that corresponds to 10% of the corresponding vibration period. 1/4 is given by the red curve, and then we have 1/2 of the vibration period for the box load by the magenta curve. And let's take the magenta curve first. So you can see a quite flat initial slope, and then we'll get a fairly limited vibration amplitude. So if you apply your load, and remember that loading magnitude, F tilde, is the same in all three cases. So you see the boxes in here, you have a low but wide box for the long half period magenta load. Then you have for the quarter load application, you have a double up in the amplitude, and for the blue curve you have once more an increase by a factor 2.5, but you also have a reduction by a factor of 2.5. So in here, there's no doubt you're very close to an ideal impulse. So when you reduce the loading magnitude from half period to quarter period, you will see a steep increase in amplitude. But the maximum also appears at an earlier time because you apply all your load faster than for the magenta curve. And when you then even increase to 10%, the increase in amplitude and the shift of the maximum is not as substantial as we saw from 1/2 to 1/4. And the shorter we make the impulse, the closer we actually get to the solution obtained by the impulse response function that we had from our first initial solution. So again, the impulse response function seems to be quite representative as long as your loading is within 10, even 25% of the corresponding vibration period for the structure you are analyzing. Now all these time loading increments starts at time equal to 0. That means that they will have shifted times when their maximum will occur. Now academically it's of course interesting to have a look at where does this shift come from and can we compensate for it. In reality, you have your load applied at some time instance and it's not really relevant to shift it. But now, just for the reason of comparison, let's try to do the following. Let's try to have the center of the box at time equal to 0. And also for the red box, it's also centered at time equal to 0. And the very short 10% T0 impact is then also centered at time equal to 0. And suddenly, we see that although the magenta curve starts earlier than the red curve and the blue curve, they all seem to have the maximum at the same time. So when they leave their loading period, we will of course have free vibrations, and these free vibrations are then occurring with maximum and minimum at the same time instances. So if you want a reasonable or consistent comparison of the amplitude and its dependence on the time duration, remember to center your box load around your initial time tau, which in this case is equal to 0. This actually finalizes this fairly short lecture on transient loading, and I say short because transient loading is basically everything else than periodic loading, and there are many different types of transient loading. And already for harmonic response, we saw that if we didn't really apply the harmonic load exactly at the resonance load, so that we got a nice build-up of amplitude, we had a transient part in the beginning where the response could actually be larger than the response for the steady state and subsequent steady state part. And we devoted this initial transient to the beating phenomena of harmonic motion, and in common language, this part will actually represent the transient part. So an example is sketched here. We apply harmonic loading, we see this initial part, but because we are not exactly at the resonance frequency, we will have a beating phenomenon here, but then we will move into the steady state amplitude part that is governed by where we see the amplitude is obtained by could be checked or is given by the frequency response function, but often this initial part here is actually referred to as the transient part. So that is the part where the initial conditions are dominant. Or the terms containing the initial conditions are still part of the full solution. They all contain a term with a decaying exponential function. So as time progresses, this factor here will of course approach 0, and that means that the transient part with the constant harmonic amplitude and a period that is equal to 2 pi divided by the forcing frequency will be the full solution, the steady state part, but the transient part in the beginning actually provides the largest amplitude. So this is for an omega that is not equal to the resonance frequency omega 0. So there are many things referred to as transient response, transient part. It refers to initial conditions, it contains impact loading, it contains non-period loading, box loads, constant loads, and that's why we have only considered a few things within this large umbrella of transient loading.